It's basically the first day that is managed by the teams. So we have Samuele and Lukas' team today, and then the three other ones in the coming days. And today we will have 4 excellent speakers. So in the morning, well, I don't know if in the morning, but Lukas will speak sometime in the morning or in the afternoon. And he's basically the main brain of this group. So Lukas did his PhD here at BUT, but he spent quite some time in Hinek's lab in the old days in Oregon, and then he was like more than a year with SRI in Palo Alto in California, and he was behind like some pretty important things in the area of speech processing, like Caldi toolkit, iVectors in speech recognition, and so on. Samuele is a postdoc research associate at CMU. In Shinji's lab, basically, to put it short. And he's doing speech recognition, also machine listening. Samuele is originally from Italy, from Università Politecnica della Marche. My Italian pronunciation is not perfect. And he's behind a couple of also very important things in speech, like SpeechBrain, ESPNet, and so on. Yoshiki Masuyama, I hope I got it correctly, the name, is from Tokyo. So he's in Merl, in Mitsubishi Electric Research Laboratory, and also with the Department of Computer Science at the Tokyo Metropolitan University. And he's into audio signal processing, multi-channel speech separation, and many other things. And in the afternoon, there will be also Alex Pollock. So I will introduce Alex right away in the morning. He's a junior researcher and PhD in our group here at BUT. His research focuses, as you might imagine, speaker-aware automatic speech recognition or speech recognition combined with diarization. And despite his very young age, he already got some accolades like the talented stipend from the South Moravian region and so on. So I stop here. I think we don't have Radim here, so we have no practical info, so we can run straight to the technical program, and I pass it over to Samuele.
It should work, yeah, right? Yeah. Okay, cool.
There was actually some kind of
what?
I think it's better to put it because now it is very sensitive to the breath.
Okay. Yeah, I know. Okay, cool. It will fall again probably, but yes. Okay. Yeah. Thanks, Sondra, for the very nice introduction. And yeah, as you said, I will do this presentation this morning with Yoshiki, and then in the afternoon, Lukas will present. We will talk about the work with DCAO, the target speaker ASR, and Alexander will have a very great tutorial and also a little bit of a little competition between the people, like to improve target speaker ASR. So yeah, we are all part of the EMMA team, end-to-end multi-channel, multi-talker ASR. We're a big team, like so many people will be part-time, like in the following weeks. And yeah, as the picture implies, I stole the picture from Yoshiki, by the way. Yeah, it's we concern mostly about meeting transcription. So like you have an array device, and then you try to recognize and transcribe the speech from multiple speakers. So yeah, I started working on speech actually at 6 years ago at the JSALT 2019. So some of you were there, like we were in Montreal, and at the time I was an undergrad student, like many of you. So and I worked on a very similar topic actually. microphone arrays for ASR. So this was again, like multi-speaker meeting transcription and so on. So it's a great privilege to be here, and I'm sure that many of you will have very good careers in the speech community and so on. So the table of content of this morning, I will give a brief introduction on what is the problem, what's difficult about the conversational speech recognition and in the wild everyday speech recognition, and give an overview about the data set, the benchmarks over the years, like 20 years, and what evaluation metrics are used, and then we will move to the technical overviews, and Yoshiki will present we'll talk about mostly front-end processing methods, so methods that rely on the array processing or not strictly ASR, so before. And yeah, I have put also a link to these slides, by the way, if you want to follow. And yeah, all the references I put links because it's quicker. It also occupies less space. So yeah, first, does it really make sense to work on ASR today? No, sometimes I have some friends from NLP community. They say, my phone is pretty good actually. My father thinks I will be jobless. And I mean, on some benchmark data set, the past 10 years, we made huge progress. We are about human level performance. So, and if you think about Siri or Google, the assistant, when speaking to your phone, it's actually pretty good. This is a reason to work from OpenAI Whisper. You may know it, or you may not know it. So they train this model. It's an encoder-decoder model with more than 1 million hours weekly supervised data from YouTube, probably. They don't mention, but it's YouTube. So, and they claim, okay, yeah, we have competitive better than human performance on several benchmark data sets. Some are very complex, like Chime6 or TED-LIUM and so on. So it's pretty impressive, the progress. But, this maybe was solved 9 years ago because there was, again, with no transformers, no end-to-end model, like DNN HMM models. There was already switchboard telephone speech. They claimed, okay, we are better than human and so on. So there are always those claims, but there are catches in those claims. Most of these claims, you focus on a single task, a single data set, and you mainly focus on pre-segmented speech. So, you have different utterances. You apply your SR model on every utterance, and you get a transcription, and then you compare the word array to the transcription. But the real word is not segmented. We have to do segmentation and so on. It's the stream of speech is continuous from recordings. One example is Libri speech. You probably know it's audiobook data, and it's less than 2% order rate, which is definitely better than me, the state of the art. And yeah, audio, I think it's not playing. So this is one example.
Southern California Edison has about a 75% interest in the plant, which is about half.
It's red speech, basically. So, it's like a F1 car. My SR model is like an F1 car. It's very highly tuned for perfect track conditions. And the audiobook recording has this perfect track, perfect asphalt. But the real world is more like this. You have potholes. It's messy. It's chaotic. And one example is Chime6 data. It's a meeting. It's a dinner party meeting between friends. And it happens in a home environment. And the friends talk with each other, they laugh a lot. They may eat, they may prepare stuff, and so on. So this is one example from the far-field array capture signal.
I think I use only the yolk, right? The recipe's on my computer. Is that how you do egg wash?
So there are 3 speakers. You can recognize only clearly the first speaker. There is another speaker in the background, which is this one, which is barely audible.
Yeah, why don't you take it with you?
So it was barely audible, but still, like, you know, if you want at some point to build a, I don't know, conversational speech assistant or a robot that can navigate the real world, we need to address these problems, like how to, you know, like recognize speech from multiple speakers, and so on. So. Yeah, everyday speech is complex. Like audiobook is only one part of the story, or like lectures, for example. You can have a noisy environment, reverberant environment, multiple interfering speakers. It's highly depend on the domain, on the situation. So we can have multi or single microphone channels, like these single microphone channels, for example, but you may have an array device there. You can have multiple microphones, or your laptop or your phone has multiple microphones now. So, and you can use those multiple microphones to do some cool stuff, like some speech separation, so on, that Yoshiki will explain later. But you can have a single device. Like, I don't know, a classic meeting, maybe you have a central device, or in a lecture you have one device. But you can also have multiple devices, like, I don't know, for Teams call, for example, everybody has his own stream. So, or I don't know, so in some situation you may have one microphone for each speaker, and this simplifies a lot the problem. And I don't know, there are some applications that, I know that, for example, Teams now support the fact that you can just turn on your laptop the Teams, and it will aid in the transcription, for example. So you can have in meetings you usually bring laptops. Anyways, you have laptops, so like you can maybe improve the transcription by using your device together with the others' devices, and so on. So, and this, by the way, was one of the, you know, like my past JSALT topic, pretty much. And yes, one thing that is highly, sometimes it's I don't know, it's not really considered in many ASR benchmarks, is the fact that they basically rely on pre-segmented data. So, and for some application, you have pre-segmented data, or it's not pre-segmented, but the segmentation is trivial. Like when you speak to a Google Assistant or a smart speaker device, you will have a keyword spotting. So the keyword spotting will, I don't know, you say, "Hey Siri," it will fire up, and then the ASR model at some point will have the endpoint detection and so on. And it's several seconds. It's highly simplified. But if you have 1 hour continuous recording of multiple speakers, yeah, that's quite difficult. You need to segment each utterance from each speaker and so on. And then you have to also do diarization, like Federico Landini explained a bit. And I will return on this topic anyway. It's long form complicates a lot the problem. And there are also differences at the language level. And I would say it's on the paralinguistic level, because the setting will highly influence the amount of overlapped speech, the amount of laugh, and so on. And this complicates ASR. So colloquial speech is much more difficult, no? It's you speak more. I don't know. I will speak very differently from a lecture than with my friends, and you will have a faster undertaking, lots of laugh with your friends, and so on. And this will break the ASR model. So it will be very highly dynamic. And while a lecture is not very highly dynamic, it's much easier as a scenario. And the overlap speech is pretty hard, because you can have short back-channel responses, such as, oh, no, yeah, oh. So, and these will come in the middle of the utterance of the other speaker. And this could break diarization. It could break the ASR, for example, because it may confuse it and so on, especially if the ASR model is only trained on single speaker data, like from libre speech and so on, where this doesn't happen at all. So and you may have interruptions. And so it's complicated. And the fact is you don't think about it, but it could be 50% of the whole speech duration. So it's quite a lot. If you I don't know, even if you recognize perfectly all the single speaker data, you will still do 50% errors and so on. It depends how many words there are, but it's significant actually. So, and of course, like AMI is like a meeting scenario in office meeting scenario. Chime 6 is the crazy dinner party scenario. And the crazy dinner party between friends is a more overlap speech, of course, because it's, it's more dynamic conversation. And regarding applications, human-machine interaction, you have pre-segmented short-form recordings. Keyword spotting makes the robust ASR job much easier. And we may not care about exact transcription, actually, because if the goal is like feeding the transcription to a large language model, the large language model can tolerate a lot of errors. I can just, when I ask to ChatGPT, I will write in the worst possible grammar ever, and it will understand perfectly what the task is. So we may not care about the order rate too much in this case. In other contexts like doctor-patient recording, legal meetings, office meetings, we care about exact transcription much more. So, and also automatic captioning, for example, especially for, you can have streaming automatic captioning to aid people with hearing loss and so on. In that case, it's highly important to be factual with the transcription. In some cases, no. If you have a very short meeting with your colleagues, maybe you don't care about the transcription. Maybe you just want to do the summarization of the meeting. So, and then in that case, you just feed the transcription to LLM, and they will generate a summary which will tolerate a lot of errors. I will have an example afterwards. And I also would say that aside from these applications, like being able to take everyday speech, multiple speaker speech, it's a fundamental AI problem, because if we want to have human-like conversational agents like Moshi or the new GPT-4o, like these multimodal models, they cannot now interact with multiple speakers, for example. That's a current limitation, but in the future, why not? Like, I think we can have a lot of new applications for that. And of course, like robots and agents that must navigate the real world. Like they have to be in a restaurant, they have to be in a nursery and so on. They have to understand the speech from multiple speakers and so on. So it's a fundamental AI problem. Like it's not only NLP can work on AGI. I think in the future it will be more multimodal. It will be space for everybody. So yeah, as I said, long-form audio. I will talk a lot about long-form audio because it greatly makes the problem much more difficult. And what it is, you have a 1-hour meeting. You might have multiple microphones. And then you have a utterance group, a group of utterances, and then there is silence. You have interaction between speakers and so on. And to do ASR, you will need to recognize where the speech is, who is speaking when, and then feed the ASR model and do the transcription. So the end goal is a rich transcription for meeting transcription. So it's just not ASR. So it's like Whisper, OpenAI Whisper does only ASR, for example. But in a real application, we would like to have who said what, like diarization, so speaker attribution. And also temporal localization, because maybe for some applications, we want to double check if the transcription is right, or we may have some accountability, like you want to double check where if the transcription is correct, especially legal or doctor-patient recording is very important. So but play your part knows much better than me how important it is. And so one example of The system hypothesis in this case could be like a JSON file, where you have for each utterance, this is the output of your system, you have the start time and time for each utterance, the words, and the speaker. And so the most trivial way to do it is, of course, like you first do diarization, you segment the speech and you recognize who is speaking in each segment, like which speaker, and Federico explained it beautifully last week. And then you can just feed each segment to the ASR model. And then you obtain, of course, like start and time and the speaker from diarization and then the words and so on. But it's not really that simple. And even if we have Oracle diarization, the current systems break. Like, for example, on LibreSpeech, which is audiobooks, Whisper, which is this big model trained on more than 1 million hours of data, it's pretty good. Like, it's better than human, of course. On Switchboard, which is already conversational speech between two speakers, but it's telephone, so they don't they can and they use Oracle diarization for that. It increased at 13.8. And they can still have Oracle separation because on telephone you have both channels, no, decoupled. But on very crazy like speech in the wild meeting scenario, like the dinner party scenario, like Chime 6, or even not so crazy scenarios like Mixer 6, which is an interview between two speakers. It's an interview. I will play audio examples. It's perfectly reasonable. It completely breaks, like 25.5%. Using Oracle diarization, and using also a powerful multi-channel source separation method that Yoshiki will explain. So it's not on par with human performance. Humans don't need Oracle information. Yeah, so yeah, we need to deal with noise and reverberation and multiple speakers then. If you want to tackle in the wild speech, and we need to deal with long form input. So to have a recognition, speaker attribution, and segmentation. And yeah, I will briefly explain now some data set and benchmarks. Some I already explained, like you already seen, like Chime 6, like the dinner party, or LibreSpeech, and so on. So actually, like the research in this direction comes from, I think, the early 2000s, it's most 20 years. Like, because at the turn of the millennia, with some, there was the GMM, HMM, ASR system reached maturity, and there was some advances in, for example, data-driven diarization with, again, GMM models. And so they said, oh, okay, that's cool. Like, we can tackle my meeting scenarios. And one of the first work was AMI. And it's still very relevant today. We'll actually use it as one of the scenarios where we want to evaluate our methods during the workshop. So, and yeah, it's a great data set. And during the 2010s, like most of the efforts were like on semi-simulated data. So you just simulate data from LibreSpeech, audiobooks, like with artificial reverberation and so on. And but like in 2016 and so on, Chime 5 and 6 and Deep Code, these dinner party scenarios, very unconstrained, like came out. And then iShell, for example, it's so not only English, but also Mandarin speech, and the Mixer 6 speech. So it's actually growing, the interest in this area. Like there have been more and more data set in the recent 8 years, I would say, like a lot more data sets. And yeah, like in the last 5 years, a lot of data sets actually are limiting and so on. Most of the data is, by the way, English or Mandarin. We don't have really multilingual data. One cool new application is a new domain. Aside from meetings, is okay, Meta has these AR glasses, and they are really interested in doing ASR, for example, with these AR with these glasses. Or even Google now has interest, like for streaming audio captioning and so on. So like Ego 4D, for example, is a huge data set with egocentric videos, and there is a ISR track, ISR and diarization track. So it's interesting. And also we at CMU have, we made some effort like in the recent CHIME 7 and CHIME 8 challenges. Like we tried to build a benchmark for meeting transcription, like the CHIME 7-8 distant ASR benchmark. And we basically collected a bunch of data sets which have very different characteristics, like different duration. So it could be 2 hours, 30 minutes, 15 minutes, for example, or even less. Not so far, it could go like 6 minutes, I think. I mean, Alexander probably knows, and Dominic knows better than me. And then you can have different number of speakers, 4 speakers, 3 to 8 speakers. We try to build this benchmark where people cannot overfit to one domain only, because that's the problem, no? Like you overfit to one domain only, it's very easy. Like you can just tailor your approach to 2 speakers, telephone speech. It works perfectly, but then you maybe apply to, I don't know, 2 speakers, interview scenario from far field speech, it breaks. So it's very important, I think, to try to test your method on different domains and so on. And also we try to have a varying recording setup, because we thought that, it would be cool to have a model that, a pipeline actually is not a single model, that you can just throw at your recording setup and it will work, being it a label microphones or a laptop or a array system. It's, and we had some success that in the CHIME 8 Days challenge, the top systems are able to be competitive with narrow domain focused systems. So it's a viable approach to have a general array agnostic pipeline. And I will want to, I will torture your ears a little bit more, like with some audio examples, like to, I don't know, so you can understand how challenging could be those tasks, and what we will do during the workshop, like, So this is like from dinner party.
I dropped a fork in a restaurant and he was also upset with me. For dropping it or for using it after? It's like Bobby would yell at me. I'm like, it's fine.
So, yeah, this is a bit crazy, extreme example with a very bad microphone channel, but you can, there is lots of noise and lots of laugh. I mean, they're having fun, no? It's a dinner party. And this is like,
where are you from?
I'm originally from California.
That's fine. You grew up in Monterey.
So here also they are moving around stuff, and the signal is very high clipped, like it could clip if you touch the microphone and so on. So and these are very extreme cases, like these are very unconstrained scenarios with. Which are very, very challenging. Like we saw that the word error rate for a whisper was like 25 there and 36 on CHIME 6. So it's very high with oracle diarization and the multi-channel speech separation. This is like Mixer 6, it's an interview between 2 speakers.
Have you ever held office beside public defender or like any?
Well, I was state public defender. I was.
This is much more reasonable. Like, I mean, from the speakers you cannot probably recognize much, but it's 2 speakers, and one of the speakers it's much louder and so on. And still, the order rate for whisper was 25% in this scenario. So it should be much better, right? And there are techniques that could make it much better. So I will explain later. And this is the last.
Is it something man-made?
Yes. Computer?
It is a computer, but that's not the answer.
this is also very much more simple. It's office meeting and so on. But it's only corrupted with a lot of low frequency noise from probably a ceiling fan. And yeah, another thing that I want to say is that we don't have much data. Like, we cannot train system from scratch on those meeting scenarios because the annotation is crazy expensive. So you will have to have, every speaker will have like a lapel microphones like me, or better even a headset microphone. And then the annotator will have to listen to each of the speakers and annotate the segmentation and also what they said. So it's very, very expensive to collect this data and to annotate. You cannot be at scale. I think if we combine all the data sets, maybe it's a little bit more than 1,000 hours, even if we combine Mandarin data with English data. So we have to leverage a pre-trained system in some way, and then yeah, Alexander in the afternoon will show you how we can do it. And yeah, I mean, for some domain, we don't even have any data at all, like doctor-patient recording. That's why the play your part team exists. We don't have data at all. So data is a problem for meeting transcription. And yeah, I will talk about a little about evaluation metrics now. Like, as you can guess, drum roll, it's order rate, of course. Like, I will not explain it in detail. You probably know better than me, but what if we have long-form audio is actually not so trivial. Like, okay, if we have one utterance, if you have words predicted and the reference words, we can compute the order rate and that's it. What if we have long-form audio? We can have like n time start time in the reference and n time start time in the system hypothesis, but the timestamp maybe don't match because we have to do diarization and then we need to do recognition and so on. So the diarization system maybe it's made some errors, and then maybe made some errors in the speaker attribution, and then maybe we made also errors in the recognition. So how we score, how we evaluate our system. So it depends on what we have to measure, actually. Like, it depends is always the correct answer. Like, it works in every job interview. So if we want to do only a SAR evaluation, of course, you can use Oracle diarization. And Whisper paper does that. It's perfectly fine. We just take our ISR system, we use the Oracle diarization, and we apply it to each segment, and we do recognition, and we do scoring, and that's it. It's just we are back to short form ASR, no? But what if we want to do full system evaluation? Like, it's not totally clear what we can do. So we need to align the reference and the system in some way, because the system, of course, will output some speaker labels, but the speaker labels will not be aligned with the ground truth, of course, because you cannot know a priori the name of the speakers. No, it's possible with name identity, transcription, and so on, but maybe the speakers will not say each other names, for example. So it's impossible. It's a permutation invariant problem, like Federico explained it for diarization, for example. And so what we can do, we can use the concatenated minimum permutation order rate. It's a very simple technique. Like, we can take the reference. Okay, we go through the whole annotation. We concatenate the utterances for every speaker. Like, every utterance are from P03, we concatenate it. We make a very long text, very long utterance. And then for the other speaker too. And we do the same for the system, like speaker 1, we concatenate the utterances, speaker 2, we concatenate the utterances. And then we do we will have these 4 utterances for every speaker in the reference and in transcription. And we just do but the speaker IDs do not match, right? It's you have P03, speaker 1, P01, speaker 2. And how we find the optimal matching? We just compute every possible matching and then find the permutation that minimizes the order rate. So it's a very simple technique, actually. Like, yeah, it was introduced during the Chime 6 challenge, so it was about, yeah, say 6 years ago. Yeah, we just find the optimal matching by the matching that minimizes the overall order rate between the concatenated utterances. But what's the pitfall of CP order rate? I don't know. This is a question. Do you know what it doesn't measure, actually? It doesn't measure sound. So it will measure speaker attribution, right? But anybody else some clue? Like, what's the issue here? The number of speakers, no, you will still account for it. I didn't show, but if you have more speakers in the reference or in the transcription, all the words will be insertion or deletions, no? Like, if you have false alarm speakers and your system will output, I don't know, like 3 speakers in this case, and you have 2 in the reference, all the words that will be given to that speaker will be insertions. So it will still account for it. But yeah, it's actually the segmentation. Segmentation, it doesn't care about the segmentation because we just concatenate. We just concatenate the utterances based on the speaker ID. So we just concatenate all the utterances. And it doesn't account for segmentation. You can basically, put whatever timestamp and it doesn't care. So usually you just combine it with the diarization error rate, for example, to see if your model at least has a reasonable segmentation. But then there are more refined approaches, refined techniques like TCP order rate, time-constrained. It's a time-constrained version of CP order rate. So they basically add some time constraints such that, okay, if the segmentation of this word is 5 seconds after it should appear, okay, I will count it as an insertion, as an error, and so on. But yeah, you will see this toolkit. It's like meetable. It allows for a very easy computation of this CP order rate, TCP order rate, or query rate. So meeting transcription metrics. Like it will be used in the tutorial this afternoon. Like it is also, you will see how like you can visualize the errors made over the transcription, like over the long form audio and so on. It's pretty cool. And yeah, another very interesting topic is like, what about downstream tasks? Like, aside from order rate, can we use some downstream tasks like machine translation or text summarization, for example? This is a very active research direction, by the way. There are not much works on this direction. And the problem is like, okay, it's very expensive to get human annotated ground truth. I mean, if you have 1 hour meeting or even 15 minutes meeting, you can have, I think on not so far, 6-minute meeting, you have maybe, I think 5,000 words, something like that. And, you will have to evaluate 200 meetings and then pay a human to generate a summary and so on. It's very time consuming. So one way to do it is like you can use proxy evaluation. Like you can take the reference, run a summarization model, like nowadays it would be LLM, like you will prompt LLM to do it, and generate a reference summary. And then you do the same with the system hypothesis. You generate a summary, and then you compute some summarization metric like G-eval, Uneval, or or Rouge. I would not. Maybe Rouge it's a bit old, but yeah. I try to do that on not so far challenge data. So not so far is office meeting scenario. And basically, I try to take the participant systems and then feed it to Gemini, and then obtain a system summary, and then do the same with the reference, the ground truth reference, and then using GEVAL. Like GEVAL is also LLM-based evaluation score. And what it turns out is that, as I said, for meeting summarization, the transcription quality, it's not that sensitive to the transcription quality. Like you have the top scoring system, like from USTC and XLib, and you may have some, and this is like the TCP word rate they use. It's like I think it's 15%, something like that. And then you will have the baseline, which is more like towards 50%. And the difference is not that crazy if you look at the summarization scoring. We have 4.1 overall and 4.3. And then I tried also to insert random errors in the transcription, like random deletion, 50% random deletion. Delete 50% of the words like randomly. It's still 3.8. You see there is a degradation, but it's not quite. I don't know, it's not very significant. The fact is that the LLM will generate a beautiful word salad, and it will still read reasonably the summary, I would say. So I think we need better metrics for summarization. But you can also see the other flip of the coin. It's like, okay, maybe for summarization, we don't need transcription. We can do end-to-end summarization. And maybe that would be the future. I mean, some models can already do, like Gemini can do, because it can ingest audio, for example. I never tried it, but yeah, I would say it's an interesting approach, end-to-end summarization. There is not much academic work right now regarding that, like end-to-end speech, meeting summarization, and so on. So yeah, but maybe like, I don't know, like Santosh or Ramani on Friday will explain a bit about in this direction. So yeah, so the basic overview is done. Like we can move on to the more juicy stuff now. Like I just have and Yoshiki will explain about the front end. Yeah, like how we can achieve robustness. Like we first need a strong diarization system, and we will not explain this. Like this was covered by Federico, like last week, and like if we have a robust diarization system, basically the problem is solved, no? Because you can just apply our ASR model on each speech segment. We know the speakers, we know where is the segment, and so on. We just apply the ASR model. Well, if we have overlapped speech, it's not that easy because we need to deal with that. It could be 50%, no? Right. So we need some techniques to deal with this overlapped speech. It's not just about diarization. We need some techniques to do speech separation or implicitly handle the overlapped speech into the ASR model. So we can categorize these two approaches on front-end based methods, like pre-processing at the waveform or input feature level. So at the feature level, basically. And this Yoshiki will talk about. Or rely on the ASR system to do implicitly the speech separation. So you don't do explicitly, like at the waveform level, the separation. Inside the representation of the ASR, in some way, the ASR will figure out, okay, I can just attribute the words to two speakers, and so on. And yeah, now Yoshiki will explain about more about the front-end processing, because he's the expert here. So yes, we'll switch a bit. Oh yeah, the microphone. Yeah, I don't know. Do you think?
Can you hear me? Is it working well? Good? No? Oh, maybe more. Okay, sorry for it. Hello? Can you hear me? Good? Okay, and also let me test the audio quality again.
He is a major figure among writers who break away from the American tradition of realism.
Was better.
He is a major figure among writers who break away from the American tradition of realism.
And pointer works. Good. Okay, so good morning, everyone. I'm Yoshiki Masuyama from Mitsubishi Electric Research Laboratories, MAR. Sorry. And yeah, it is my great pleasure to have this opportunity in beauty. And I'll cover the single and the multi-channel speech enhancement and separation as a front end for robust far-field conversational speech recognition. So before we dive into the technical content, I'd like to acknowledge my collaborators. The 5 people on the shaded area are my current colleague at MAR, and some other collaborators are actually ex-MAR. So here is the agenda of my part. And first, I'll give you a brief overview of speech separation and enhancement, or SSE. So yeah, something similar with Samuel's talk, but let's start with the challenges in the far-field conversational speech recognition. So when we have an intensive discussion, like a transformer vs mamba or something, but people may speak simultaneously. So and also the background noise and the reverberation also degrade the audio quality. So as you can see here, the far-field microphone is contaminated by various factors. So here is an example of noisy reverberant two-speaker mixture.
He is a major figure among writers who break away from the American tradition of realism.
Interestingly, humans can focus on one desired single source of interest, even this kind of the very noisy, crowded situation. This human ability and mimicking this ability by machine listening is called a cocktail party problem. And degraded speech will decrease the performance of downstream tasks like speech recognition, maybe speech summarization. And because such kinds of the downstream models are typically trained on the relatively clean, at least a single speaker data. So we would like to isolate each speaker stream from the mixture recording like this.
He is a major figure among writers who break away from the American tradition of realism.
And here is another speaker.
Origins or causes of spontaneous mutation are not yet completely clear.
This is not the clean speech ground truth, but this is a result of the speech separation. So if you are not so familiar with SSE, I hope you get a little surprised about the separation quality. Good. So let's think about how audio mixture is recorded by microphone. The acoustic propagation from source position to microphone is typically characterized by the room impulse response, or RIR. RIR is a time domain filter that mimics the transfer function, time invariant transfer function. And the RIR depends on the relative position between the source and the microphone, but also it is affected by the room geometry or material of the surface. So the RIR involves the direct sound that is completely defined by the relative position of the microphone, the sound source, and also the sound speed. But the other part, early reflection or late reverberation, depends on the room geometry or room surface or anything. And this rate reverberation degrades the intelligibility of the speech, and it is harmful for speech recognition or other downstream tasks. Next, I'd like to formulate the mixing process. So again, we observe the convolution of the RIR and source signal. And here, Y is called the source image, or image of source K at the microphone N, where the K is the index of the sound source. Then the microphone will record the superposition of all the source images and possibly the background noise. The observed mixture are often transformed into the time frequency domain by using the short-term Fourier transform, STFT. You might be familiar with STFT, but let me briefly recap it. So the time domain signal is chopped into a short segment by using the sliding window, and then we apply the discrete Fourier transform. And the STFT magnitude will capture the power of each frequency component at each time frame. So it is very helpful for analysis, but the STFT is also useful for processing audio very efficiently. I will show you later. And as shown in the bottom diagram, we typically do the STFT and then somehow process the audio and process the STFT coefficients are converted back to the time domain with the inverse STFT. So one of the most popular SSE method is time frequency masking. The idea is to control the gain at each time frequency bin and suppress the interference signal if the time frequency domain, time frequency bin is dominated by the other sources. In contrast, the mask will be 1, so that keeps the original audio if the time frequency bin is dominated by the target speaker. So here the STFT of the speech and dog barking, and we observe this mixture. And to emphasize the target speech, we will take the low gain if the time frequency bins are dominated by dog barking, while it will be close to 1, the white, after the dog barking stopped. So here, our goal is to somehow estimate this time frequency mask only from the mixture. More recent method considers about complex masking because it can control the phase also. And then by controlling phase, complex masking has a potential to completely recover the original clean speech. Another popular SSE method is beamforming that leverages spatial information in the multi-channel recordings. So its basic idea is to design a linear spatial filter to emphasize the signal from a specific direction while suppressing the sound from other directions. In the time domain, it can be realized by convolving the filter at each channel and then summing up the result from all channels. In the time frequency domain, again, we often consider the concatenation of the M-channel observed signal at each time frequency bin. And then the filter and sum in the time domain can be approximated by the inner product at each time frequency bin, where this W is the filter or called a beamformer. So this time frequency domain implementation is somehow approximate the time domain process, and it is called narrowband approximation. And here our target is to somehow estimate this W only from the mixture or sometimes with additional information. So next, we'll look at the performance metrics to evaluate the SSE. And similar to the speech synthesis talk yesterday, the evaluation of SSE is actually not so simple because speech contains speaker information, the linguistic information, other kinds of information, so it is not so simple. So there are several ways to categorize the SSE metrics, but here I'd like to consider the intrusive and the non-intrusive metrics. Intrusive metrics require ground truth signal. And I mean the pairs of the clean speech and its degraded mixture. I think the simplest intrusive metric is SNR, and all of you guys are familiar with that, I guess. But in speech separation, we typically use scale invariant SDR or SISDR. SISDR compensates the scale difference between the estimate and the ground truth before calculating SNR. This is because for human perception, even after changing the scale, the clean speech is still completely clean. So I think this is very natural metric. Meanwhile, the PESC and the STOI are metrics for evaluating speech naturalness and intelligibility respectively. But these metrics are still based on the clean speech, clean counterpart. In contrast, the non-intrusive metrics do not require ground truth, so you can evaluate the speech enhancement or separation model only with the enhanced and separated speech. For example, the touch audio screen is a neural network-based estimator of the SISDR, PESC, and eSTOI. So the network can be trained with pairs of the noisy speech, clean, and its counterpart clean speech, and also the speech separation model. And you do the speech separation and check the SISDR or PESC or eSTOI with separated speech and clean speech, and train the neural network to predict the score only from the separation output. And after that, you can evaluate the separation quality with other mixtures. Meanwhile, the DNS modes or UT modes are designed to predict the scores of human subjective evaluation. So it needs a subjective evaluation score also. And in the literature, sometimes people organize some challenge first and then get enhanced speech from many participants, and then do subjective evaluation, and then train the model to mimic the scores. This kind of cycle is now very kind of popular in various tasks, including speech synthesis and maybe enhancement. And in my opinion, the word error rate or speaker similarity can be seen as something in between them. For example, we can compute the word error rate only from the enhanced speech and its transcription. So we do not need a clean speech. So actually, the clean speech is very difficult to get or obtain. So I think that this is a very auxiliary evaluation metric. And these kinds of the non-intrusive or word error rate are very useful to evaluate enhancement or separation performance in the realistic situations like ARMY or CHIME6, as Samuele mentioned. Okay, so if you want to start SSE, there are several greater open source toolkits supporting it. For example, the Asteroid focuses on SSE, and in my opinion, it is very easy to start. And SpeechBrain offers tutorials for various speech processing tasks, including source separation. And I think the ESPNet SE is the most comprehensive one. This is because ESPNet covers various downstream tasks and allows you to integrate your SSE model and the downstream model, and you can fine-tune the entire system in an end-to-end manner. I'll show you later, but the joint training is very helpful to improve the performance. And the last one, the Pyrum acoustics, is a bit different one. It provides a RYR simulator based on the image source method, And it also supports several array signal processing methods like beamforming. And regarding the data set, Samuel already mentioned a good robust ASR data set. But in addition, there is a series of artificial mixture like based on the WSJ corpus, like a WSJ mix or WAM and a WAM-R. And these kinds of the artificial data set is helpful because it allows us to evaluate the intrusive metric. So that it is much more, allows us to much more precise evaluation. And if you cannot access to the WSJ corpus, there is a good counterpart based on the Libri speech. It is called a Libri mix. So you can, maybe you can start with download the asteroid and simulate a Libri mix, and then train your model as you want. So okay, let's move to the detail of the single channel SSE and its training tips called permutation invariant training. So again, the estimating the time frequency masks is de facto standard in the single channel speech separation and enhancement. The network will take the features of the mixture like a log magnitude spectrogram and output mask for each speaker. As a training target, various ideal masks have been developed, like a Wiener mask, ideal ratio mask, and phase-sensitive mask. And here, the ground truth ideal masks are computed from the Oracle sources. And phase-sensitive mask is achieves the best SNR in terms of among the real value time frequency masks in the time frequency domain. But meanwhile, you can also convert the masked STFT coefficient Gx here, and you can compute the loss function in the time domain with respect to the ground truth. And for example, one of the metric SSDR is what we want to maximize, so that we typically use a negative SISDR as one of the loss function. So going beyond the time frequency masking in the STFT domain, the masking in a latent domain has been developed where the STFT and its inverse are replaced by the trainable 1D convolution and the 1D deconvolution encoder and decoder. This approach was first proposed by Luo in the CompTasnet paper, which is very, breaking through paper, because as shown in this bottom table, the CompTasnet outperforms some kinds of the ideal mask. Here, the WFM means a Wiener mask. But yeah, since the non-negative time frequency masking in the STFT domain couldn't control the phase, so its performance is somehow limited with resolution of STFT or other conditions. But by optimizing these encoder and decoder together with mask estimation network, the CompTasnet achieved better performance. Then the dual path modeling was also proposed by Luo to handle a very long sequence by segmenting the frame into chunks and performing the intra-chunk and inter-chunk modeling. Here, the intra-chunk model focuses on the local modeling, while the inter-chunk model performs the global processing, but with chunk level time resolution, I mean the low resolution. And this is especially important for the end-to-end latent domain approach because the frame length of this 1D convolution and the 1D deconvolution is typically much smaller than the STFT. So for example, STFT will consider about maybe 32 millisecond or 16 millisecond window. But since the training becomes unstable, 1D convolution or 1D deconvolution think about maybe 1 millisecond or possibly like only 8 sample or something. So as a result, even 1 second audio could be more than several thousand time frames. So it is not easy to handle such kind of a long frame directly with transformer or LSTM. So this slide shows some kind of timeline of notable neural network architecture in SSE. So the temporal convolution network, or TCN, is popular in speech enhancement, as you can expect, and where its duration is often doubled in each layer to include its receptive field. In speech separation, LSTM is actually still very powerful, while the other speech processing tasks are somehow dominated by transformer nowadays. But of course, transformers have been successfully applied to the speech processing, speech separation, and in both STFT domain or time domain. And the newer efficient sequence models like Mamba is also used now. And so I think that Mamba is a good fit for the SSE because RNN like LSTM is still very strong in this domain. And Mamba can be interpreted as a gated version of the linear RNN. And here is the current state-of-the-art model for the single-channel SSE. And it is based on the complex spectral mapping. So in complex spectral mapping, just the network takes the real and the imaginary part of the STFT as input and predicts the complex spectral for each speaker directly. And also, these kinds of the state-of-the-art models perform the time-frequency dual-pass modeling. So first, we encode the STFT of the mixture and obtain the embedding for each time frequency being like the 3D tensor with a time frequency and its embedding dimension like D. After that, we perform the sequence modeling along the frequency axis or time axis, where each frame or which frequency band is handled separately with the shared sequence model. And this architecture becomes popular by TF-GridNet, but again, the TF-GridNet relies on the bi-LSTM for the sequence model. But nowadays, a combination with the multi-head self-attention and some local modeling by convolution-based switch glue achieves the better performance in several benchmarks. So once you obtain the output from the mixture, we would like to compute the loss function with respect to the ground truth signals. But as Samuel mentioned, sometimes the order of speaker is not well defined. So, but during training, we must align the network output and the reference to compute the loss function. And so the permutation invariant training, PIT computes the losses for all possible permutation and try to find the best permutation in terms of the minimizing the total loss function. And after finding the best permutation, we just do the back propagation with the specific permutation. So one of the variants of the speech enhancement and separation is the target speaker extraction, TSE. TSE focuses on the single desired speaker specified by some cue, like the enrollment speech, so the target speaker's speech in a very short segment, or visual information, or sometimes timing information. So in TSE, the network is often conditioned by the encoded cue and just outputs the target speaker stream. So that there is no permutation problem. And also, it is very preferable because we don't have to care about number of speakers in the mixture. Always, the model is asked to output the target speaker stream. And more recently, the encoder and the extraction network are integrated into one system, and by just concatenating the enrollment speech and the mixture we want to separate. In this case, we can potentially leverage more information by using the self-attention between the enrollment speech and the mixture. Okay, so let's move to the multi-channel part with signal processing. So again, I'd like to recap the mixing process of the multi-channel audio. The source image of each speaker is given by the convolution of the RIR and the source signal. And we observe the superposition of the source image is Y and the background noise N. And then this process can be well approximated by these equations in the STFT domain. And our goal is to estimate this source image YK from the given mixture X. These are all the multi-channel, so like a complex valued multi-channel vector. And again, the beamforming is one of the most popular methods for the multi-channel case. And in the STFT domain, the beamforming is realized by taking the inner product between the beamformer W and the STFT of the mixture X. So the problem is how to design this beamformer. And I think that delay and sound beamformer is the simplest one. It relies on the time difference of arrival, TDOA. And like the sound from the right side first arrives the rightmost microphone, then reaches the other microphones. So there is a difference in the time of arrival. And this given array geometry and possibly the sound source direction, we can compute the TDOA for each microphone like this. And in the time frequency domain, this delay can be compensated with phase shift like this. And this kind of the vector is called a relative transfer function because it characterizes a difference between the transfer function from the source to the microphone. The delay and sound beamformer compensates the TDOA and then taking just the average. So the target signal is preserved because we compensate the difference between channels first. And it recovers the original signal. And actually, we can ensure it mathematically like that. YK is a target source image. And when we apply the beamformer given this one to apply the source image YK, we actually just recover the original source image. So this means the delay and sound beamformer doesn't distort the target signal. On the other hand, interference signals are averaged with some phase difference so that they are not aligned. As a result, by taking average, they should cancel out each other. Delay and sound beamformer is one of the fixed beamformer. I mean, its design is independent of the given mixture. And as a result, its performance is typically insufficient. To mitigate this limitation, an adaptive beamformer called minimum variance distortionless response, MVDR beamformer has been widely used. So MVDR beamformer aims to minimize the power of the interference signal in the enhanced beamforming output while preserving the target speech is not undistorted. And in this time frequency domain formulation allows us the analytic solution like this, where the VK is called the spatial covariance matrix. And then we use some of the covariance metrics along the interference signal to design this beamformer. And the VK SCM can be interpreted as intuitively. This is just covariance matrix of the source images when assuming their mean is just 0. And through this optimization, the obtained beam pattern becomes like this, so that it will take a large gain, or actually the gain should be 1 for the target speaker's direction. Meanwhile, the MVDR adaptively steers its neural to the low gain to the interference direction. So this is the key of the MBDR compared with the delay and sum beamformer. And here is another formulation of the MBDR. It relies on the SCM instead of the RTF, relative transfer function, of the target source signal. This is sometimes useful because the SCM is easier to estimate, especially with the time frequency mask. But if you want, you can estimate RTF from the SCM by using the eigenvalue decomposition. So anyway, so once we obtain the SCMs on the RTF, we can perform beamforming. So how can we estimate the SCM over RTF? One naive approach is but the practical approach is to find a single speaker segment and calculate the SCM. Maybe in realistic discussion situation, we can somehow find a single speaker segment with diarization model, and we can compute the SCMs. Another approach is called blind source separation, or BSS, that aims to estimate the spatial characteristics, SCM, and the source information only from the observed mixtures. Here, I'd like to introduce one of the widely used popular BSS method called the complex Gaussian mixture model, or CGMM. So the CGMM represents the STFT as a mixture of Gaussians, as you can infer from the name. And the CGMM assigns one source to each time frequency bin, motivated by the sparsity of the speech in the time frequency domain. Yeah. So the one interesting point compared with other GMM model, here its mean is always 0, regardless of the sources, but we formulate the variance as a product of the non-negative scalar lambda and m times m positive semi-definite matrix V. This is the SCM. So this part models the time-varying SCM as a product of the speaker activity at each time frequency beam and time-invariant spatial information. So that maybe this is not so rigorous, but here is some kind of view of the model, this model. So that we would like to, this is a distribution of the mixture, and you can find two Gaussians. And we would like to fit one Gaussian for each correspond to the speaker. Then its data generation process is given like this. Here we sample the latent speaker indicator Z from the categorical distribution. Here Z takes 1 for the target each speaker and 0 for the others. And then after that, we sample the mixture itself from its corresponding Gaussian distribution. And we would like to just estimate its parameter, the pi, lambda, and V, by using the EM algorithm. And the parameter will be estimated in a maximum likelihood manner. And the EM algorithm alternately updates the posterior distribution of this Z, like variational posterior, and parameters theta to maximize the evidence lower bound. So that we just alternately perform the E step and M step, as you know. It is just similar to the other Gaussian mixture model. And I would like to just note that so maximization of elbow in the E step correspond to the minimizing the divergence between the posterior and the conditional distribution of Z given by X and the current parameter theta. So we can just use this PZX theta to update the variational posterior. And otherwise, M step is a bit complicated in terms of the mass, but you can derive these kinds of the equations. So that we just alternately updated the Q and the lambda V pi several times, like several tens or maybe 100 iterations. Next, guided source separation, or GSS, enhances the CGMM variant called CSCGMM by incorporating the diarization result. So in GSS, we first obtain the speaker activity from the diarization module. It could be the neural network. And this tells us when each speaker is active and when each speaker is not active. And we can put this result of the diarization better as a prior for the latent indicator, the Z, so that this pi will become the time varying one. And this time varying characteristics is tying the frequency subbands. And in recent chime challenges, GSS with its accelerated implementation has been very standard front end for far field SR. And I think it is not easy to see, but here's a summary of the recent chime 7 and the chime 8 challenges organized by Samuel. But all the submissions actually somehow relied on GSS, or almost all just use GSS. So GSS is very powerful, especially with very powerful diarization module. And apart from the CGMM-based method, independent vector analysis, IVA is another prominent BSS approach. IVA extends the independent component analysis by modeling the dependency across frequency bands. So that by assuming the number of speakers is equal to number of microphones, we can model the mixing process with the mixing matrix H, and we would like to estimate its demixing matrix, so the inverse of H, as W. And IVA jointly estimate this demixing matrix and time varying the speaker activity lambda under the assumption of the statistical independence between each source. So we can derive the bit complicated, but this optimization problem. And we can solve this problem by using the measurization minimization algorithm. It is some kind of the variant of the EM algorithm for the CGMM. So still needs iterative optimization, but this approach also gets the spatial information or separation filter itself through the optimization. And the IVA is sometimes preferable because the CGMM assumes the sparseness of the time frequency speech as a time frequency bands. So it just assigns each time frequency band to each speaker in terms of the probabilistic model. But the IVA explicitly handles the overlap at each time frequency band. So IVA is sometimes preferable if you want to handle completely overlapped speech data. And before concluding this signal processing part, I'd like to mention the reverberation. So late reverberation degrades the speech intelligibility again, and also the ASL performance is also affected. So we would like to remove this late reverberation. So that it can be characterized by the clean source signal at the previous segment, and some kind of the transfer function, like this blue arrow part. And one of the popular reverberation method is called WPE, and it aims to suppress this late reverberation by subtracting the filter version of the past observation. And here the lambda is again some kinds of the time varying weight or power spectral density. And yeah, WPE is also very widely used chime challenge. Well, sometimes if you say the guided source separation, it is a combination of this model and the WPE as a front end. And also even the Google Home acoustic modeling paper mentions the WPE. So I don't know, but possibly the WP is used in Google at sometimes. I don't know. Okay, so let me summarize this signal processing part with pros and cons in the signal processing based method. So one of the advantages is we do not have to care about the train test mismatch because we always adapt the probabilistic model to the mixture at the test time. And some kind of special probabilistic model is very robust to any kinds of situation. But sometimes the assumption of the special model might not satisfy in complex situations like many models assume the scene is completely static, so speakers do not moving around like that. And also sometimes the model like IVA rely on the manually designed speech model like a sparsity or low rankness or something like that. And they have gap from the real speech characteristics. Also, the signal processing-based methods rely too much on the spatial information, in my opinion. So their performance is really limited when the number of microphones is like 2 or 3 or something like that. And actually, the IVA and its variants cannot handle the underdetermined situation. So that when the number of microphones is less than speaker, the IVA is not applicable. So I'll introduce some DNA-based multi-channel SSE methods. So instead of CGMM, we can leverage the powerful mask estimation network that was trained on a single channel data to compute the SCMs. And since the mask indicates the time frequency being dominated by the target speaker, we can mainly use such kinds of the time frequency being to compute the spatial statistics of the target speech VK. And this approach is advantageous because the network can be trained with single channel data. Maybe you can easily collect such data. While we can still perform the multi-channel processing during the inference. And empirically, it is known that this mask-based beamforming is really robust thanks to the well-developed beamforming criteria and based on some spatial statistics. But the ideal mask designed for the single-channel SSE could be not optimal for estimating spatial covariance matrix. So we can train this kind of mask-based beamforming in an end-to-end manner by using the backpropagation from the signal level loss function. Like the SCM calculation, the beamforming is a bit complicated, complex value processing, but they are still differentiable in terms of the deep learning. But I would like to note that typically this beamforming part relies on the inverse of the spatial covariant matrix, and its computation is really easily unstable. So we typically add some kind of epsilon to avoid the inverse getting unstable. But anyway, there is some tricks to handle such kind of an issue, but we have to be careful about that. And this method inherits some kind of pros and cons of beamforming, so that it is still robust to the domain mismatch and compatible with a different number of microphones. But its performance is still limited in underdetermined situation because the final output is still obtained by the beamforming. In contrast, of course, there is a fully neural approach called like a multi-channel complex spectral mapping. It is, again, very simple. Its input is just concatenation of the real and the imaginary parts of all the channels, and then just output the real and the imaginary part of each speaker at a reference channel. So this is looks easy, but actually it is very powerful because it can perform the much more complicated spatial, temporal, spectral filtering process. And it can more aggressively suppress the interference signals. But yeah, it can introduce additional processing artifact. It is typically very harmful for SR, and it is less robust to the domain mismatch, like array geometry or speaker microphone distance or anything. So the training of this multi-channel complex spectral mapping typically require a huge amount of the data to stable its performance. And one of the limitations of the typical multi-channel complex spectral mapping is just concatenating the feature in the early stage of the convolution. And as a result, the typical model does not generate to the different number of microphones. And to address this limitation, the transform average concatenate was proposed. So that it uses average pooling to gather the information between channels. And yeah, average pooling is a permutation invariant. It can generalize the arbitrary number of microphones so that you can use an arbitrary number of channels, even different number from the training and the inference. So that in addition to these supervised training, unsupervised training of SSE, especially based on the spatial information, has been studied. So unsupervised training is advantageous, especially in the multi-channel scenario, because we typically rely on the simulation to prepare the pair of the noisy multi-channel data and the clean counterpart. But the multi-channel simulation is still not so good, and we typically struggle to the sim-to-real gap. In contrast, we can record a multi-channel mixture relatively easily because microphone array is not so expensive nowadays. And we can train the network on just a mixture itself, or we can fine-tune the model pre-trained on the simulated data. And one of the early study in this direction is so the neural network will estimate the time frequency mask, and this method interprets the mask as the posterior of the latent indicator of the CGMM. And then it do some steps of the EM algorithm, and then we can obtain all the parameters for the CGMM. And after that, we can compute the likelihood with respect to the mixture itself. So this method is still based on the signal processing.
Yoshi,
Okay.
Does it have a problem also when the speaker moves? Because you train, right?
Yeah, exactly. In this method, the method is based on the CGMM, and it assumes the static environment. So still this method, is not so generalizable to the moving speaker situations. Good point. Thank you. And in this case, this method was evaluated on the Chain4 dataset, but its performance is still not as good as the supervised training, but it's almost comparable, and it clearly outperformed the original spatial model, like CGMM. This could be because during the training, the mask estimation network will see the bunch of the multi-channel mixtures, and it can learn the speech characteristics and the overlapping pattern from the real data. And another unsupervised training is based on another well-developed spatial probability model called FCA, and it is called neural FCA. And its objective is still reconstruction of the input mixture. So this is VAE, so its target is maximizing the elbow with respect to the mixture again, similar to this method, but the probabilistic model is just replaced by FCA. And it's a neural network is this part and this GF, and this inference model or encoder of the VAE will predict the latent feature for each source. And then the source decoder will propagate the source speaker activity for each each speaker or each channel. And then additionally, we provide the corresponding spatial covariance matrix SCM with the EM algorithm. So something similar to the CGMM, but this FCA is similar to the IVA. It can handle effectively handle the overlapped speech. And the last one is also unsupervised, but not relied on the probabilistic models. So this reverberation and supervision, RAS, leverages a two-channel mixture to train your monorail separation model. And the DNN is trained to separate the left channel so that the reconstruction of the right channel will be easily realized. So since the transfer function from the source to the microphone is different for each speaker, reconstructing the right channel mixture from the left channel mixture is difficult. But if we can separate the left channel mixture, it can help. It will be helpful to reconstruct the right channel mixture, especially when the transfer function is completely static again. And actually, this is not so trivial, but its extended enhanced version is very close to the supervisor training. So again, this is still trained, evaluated on the simulated data, so we can access the ground truth and we can perform the supervised training. But if we move to the real meeting scenario, we couldn't obtain the ground truth data. So maybe this kind of unsupervised training is helpful to adapt your model to the real situations. So finally, I just want to introduce some additional topic or a bit of fun example of the speech or non-speech separation. So, in the training of the SSE models, we typically use a signal level loss like SISDR or its variants. But such kind of the signal level loss function may not be optimal for the downstream ASR model. So the one common approach is a joint training of the SSE and the ASR model. It means do the back propagation through the ASR decoder output to the speech separation model itself. And it is beneficial because the SSE model is optimized at the front end of the ASR. And also, ASR model will be robust to the artifact caused by the enhancement process. And we have pushed this direction, especially with the WebLM-based ASR model. And our system keeps the modularity, as you can see here. So still just a combination, but we do the end-to-end training. So since we keep the modularity of the SSE and ASR models, we can easily use pre-trained SSE or ASR models. So the top figure depicts the pre-training process and where the SSE and the ASR models are pre-trained with popular loss function. And here, maybe we can use the single speaker corpus like WSJ or any Libri speech or anything. Or maybe you can replace this part with Whisper. And after that, we combine the system into the one end-to-end system, and we provide the noisy multi-speaker mixtures, and separation will provide output multiple streams, and then the ASR part recognize the output of the speech separation, and then do the back propagate loss function defined on the ASR output. And here the experimental result on the 1R dataset. It is a noisy reverberant one. Let me play the audio example.
He is a major figure among writers who break away from the American tradition of realism.
Yeah, again, this one. And actually, I think the final result obtained by our model looks good because although the audio is regulated by noise and reverberation, but still performance is okay. And you can find that just combining the pre-trained model, it works okay. But by fine-tuning ASR models, I mean the ASR model will be adapted to the separation output. The performance is dramatically improved. But for the fine-tuning SSE models at the front end of ASR, we can see the additional improvement in terms of the word error rate. But meanwhile, this adaptation will regulate the enhanced speech enhancement or separation performance because now the speech separation or enhanced model that is not restricted to the signal level accuracy, and it can provide additional information by provide some additional information to the enhanced speech, or maybe just the gradient from the WebLM is not so clean, maybe very noisy, I guess. And actually, I also tried WebLM fine-tuning in this context, but it will easily overfit to the training data in my experience, but maybe there is some good technique to avoid the overfitting. Okay, the last part is a bit more interesting one, I guess. Just a demo for the several applications, but the speech separation is also now considered a non-speech data set. Maybe the music source separation will take the music signal, and we would like to extract each instrument and vocal. And the universal source separation would like to estimate each sound effect in the mixture. And maybe another one actually proposed by Mal, but is a cinematic audio source separation. It will separate speech, music, and other sources like sound effects. So let me play this demo video.
Hi, Phil Swift here for Flex Tape, the super strong waterproof.
So now this marker moved to the speech side, and then the speech signal is extracted.
Tape! That can instantly match.
Then music signal is extracted.
No ordinary tape. Its triple thick adhesive virtually welds itself to the major damage. But Flex Tape grips on tight and bonds instantly.
So now the source separation community would like to explore not only speech, but any kinds of the sound signals. And recently, in this direction, the task-aware universal source separation was proposed. And this task controls the separation output with runnable prompt. So in the case of let's think about this kind of task. Like in the case of a music source separation, we would like to separate the music mixture into each instrument. But in the case of the cinematic separation, we would just consider about the music mixture as it is. So the target is different in each situation. So to handle such kind of various conditions, we consider about the runnable prompt and the promptable speech separation, or just something extension of the extraction model. And we concatenate the runnable prompt vectors with the mixture, and do some kind of a cross-prompt module. Means we do the sequential modeling with respect to the mixture and the prompt, and it mix the information between the prompt and the mixture. And then after that, we perform the target source extraction model for each prompt. And it allows us to very flexible source separation. And here is a mixture.
against which it is impossible that the people of Britain-Eula should prevail.
One night when he and Winifred were sitting together on the bridge.
So maybe you can hear the speech and also background music and also some kind of noise signal. So by providing the prompt like a speech, music mix, and the SFX mix, the model will extract each signal like this.
Against which it is impossible that the people of Britain-Eula should prevail.
Then the music.
One night when he and Winifred were sitting together on the bridge.
Sorry, that is the latter part of the speech. Sorry, my bad. And this is SFX. And yeah, one interesting point is now by changing the prompt, we can further separate this music mix to the vocal and the other instrument. And this is other instrument. Not so perfect, but you can still hear the instrument sound, I hope. And we can do same thing for the other noise signal or the sound effects. Okay, let me conclude my part. So the performance of the speech separation and enhancement has been dramatically improved, especially with the permutation invariant training. It was really important to train the speech separation network in a supervised manner. And nowadays, complex spectral mapping with time frequency dual path modeling has shown very promising result on the static benchmarks. But when we consider about more realistic scenario, the real meeting recordings, the hybrid of the DNN and the signal processing are still very powerful and preferred. Like GSS is integration of the CACGMM and the neural diarization system, and it is a de facto standard in the current time challenges. And separately, the unsupervised adaptation of the SAC model has been proposed based on the spatial statistics of it is an active research topic, I guess. And today I skipped, but the unsupervised training of the single channel data is also really active field. It sounds very challenging, but actually in the 2020, the Wisdom proposal mixed it actually works pretty well, at least again the benchmark data set. So the real world data is still challenging. So as mentioned, the domain mismatch between the artificially generated data and the actual far-field conversation is completely shows the different characteristics, and also the dynamic situation, the moving speakers, or maybe microphone will be located on top of the moving robot, and also the variable number of speakers is still a challenging topic, I guess. So yeah, thank you for your attention.
Which one of the many methods you will try this summer?
What?
Because you have shown many techniques. Which ones do you think that you will try this summer?
Yeah, in this summer, I'd like to explore this. So this is much more like a fully neural network-based method, but I'd like to train this model with I'd like to adapt such kind of model to the realistic scenario with the unsupervised adaptation technique.
Because all these training methods will have the same problem, which probably are going to work as long as the situation doesn't change. You mentioned it as a problem with the signal processing techniques, but I think that whenever you train, it will also depend on what you will be training on. And you think that it would be fine for this problem which you have this year, right? Or because all this training is, I mean, of course it probably works better. However, I don't know how adaptive it is. What you think?
Yeah, a good point. Again, the multi-channel processing method, almost all multi-channel processing method relies on the situation is static. Yes. But if we can use real data, with a neural network-based method, maybe the neural network just ignores the spatial information, and then the network can just focus on the single channel method. And again, the single channel method doesn't care about the speaker moving or information, something like that. So possibly, neural network will learn how much ignore the spatial information.
Maybe put too much hope into neural network.
That's true, yeah. Yeah. Yeah, thanks so much.
I know that there is, the signal processing aspect is really interesting to me, but do you know if there exists, a hybrid approach that might, combine, prosodic analysis, seeing how speakers, understanding, the different ways in how each speaker talks, looking at actual text and understanding that. Could you, combine them? And maybe that would be even more accurate? I probably am sure that exists, but I've never looked at that.
I see. Yeah, good point, I guess. Maybe for the target speaker extraction, here I consider about the condition by visual or enrollment speech. But nowadays, there are several conditioning techniques, maybe the speaker activity, maybe the text, say the male speaker talking in some specific languages, or female speaker other languages. So maybe, we can consider about the multi-channel extension of the target speaker extraction module. But again, it depends on the situation. Like a moving speaker is sometimes difficult. But maybe one of the simplest start point is mask estimation with target speaker extraction, and then do mask-based beamforming. I think it is already somehow used in realistic situations. Yes.
So for the you just mentioned you will try, there are some challenging scenario, you said adaptation. You would like to can you explain more? Is it you train on the source domain, then you do have another target domain, then you adapt to the target domain, something like this? Mm-hmm. And what if you cannot get the target domain data in some scenario like privacy or something? How do you deal with this problem?
Yeah, good point. In that case, maybe we have to just train your model on the various domains and hope that the model will generalize to that unseen domain, I guess.
Is this this scenario recently a hot topic in the speech separation field, or the speaker agnostic ESR field?
We typically train the speech separation model with a bunch of speaker data, and hope it will generalize the unseen speaker. It is, I think, the popular training technique. And recent paper shows speaker variation is really important to develop a model that will generalize to the various data set. So again, it is important to train your model on the various data sets.
And the data set is manually created or simulated, or
sorry, could you
for the multiple domain data set, do you simulate it, collected by yourself, or how does this set up?
I mean, for the single channel scenario, there's already a bunch of the data set with various target speeches from the WSJ, Rivoli speech, VCTK, or anything, and also noise signal is from YouTube, the FSD, or WAMR, so that we can just combine these signals. But in the case of the multi-channel scenario, the simulation is, I think there is not so many good simulators, so domain mismatch is very critical, and that is one of the reasons why we would like to adapt the model to the target domain with unsupervised manner. But if we cannot access to the target domain data, it is very challenging scenario, I guess.
Yeah, okay.
Maybe you can just fall back to the signal processing technique. It is very robust. It is a well-known thing. This kind of mask-based beamforming is very promising, I guess. It works pretty well in relatively easy situations like a single speaker or maybe two speaker, but you can use 8 microphones or something.
Okay, I see. Thank you.
Thanks so much.
Thank you. You mentioned one of these techniques, which is when you train both the separation and the recognizer. How much data you need for that? Because wave LM typically requires quite a bit of data, right?
Yeah, so in this case, we use a popular speech separation data set called WAMR. It is about 20K mixtures or just short utterance from the WSJ. Mm-hmm. So its training is, I think this is still manageable with limited resources because we just borrowed the pre-trained WebLM, and WebLM is completely frozen during this training. Mm-hmm. So we don't have to care about the training data.
See, this is frozen, I know.
Yeah.
I didn't know.
Yeah.
I'm sorry.
Okay, yeah, no problem. And then we just trained the ASR part on the WSJ first, and the separation part is also pre-trained, and then just fine-tuning in the end-to-end manner. So the training is almost dominated by this pre-training stage, and the fine-tuning is almost like a 10 epoch, or that is enough.
And the input to this technique is a waveform?
Yes, or could be the STFT domain.
STFT, so it's not a time domain.
Yeah.
It's a short time Fourier transform?
Yeah, in this case, this separation network is a STFT domain one, so we pass the STFT coefficients, and we do separation, and we have to convert it back to the time domain, because then we have to pass the separation output to the WebLM. Yeah. So it is a bit complicated pipeline, but we can still perform the back propagation according with this pipeline. And then it actually helps in the static environment.
Well, how long is the input? How long is the...
in this data set, audio is typically 5 seconds or something.
I know, but you take short segments, right?
Yeah.
Like 20 milliseconds or something to compute time frequency pattern?
The time frequency pattern is like, I think the 32 millisecond window.
How?
32 milliseconds.
32 milliseconds.
Kind of with half overlapping. Yeah, maybe we can discuss more later if we want. Yeah, I'm happy with that. Yeah, we can take that.
minutes break.
Thank you again.
Make sure it works. Huh? Yeah, it works. Yes.
Is that yours? Or? I think it's mine. Okay, cool. All right, guys, let's settle down. All right.
Okay, yeah, I'm back. Yeah, like Yoshiki explained a bit about front-end methods, right? And so I'm back for the back-end methods, but my overview will be more like more on the broad abstract side. I will not delve too much into each method. Maybe on just two methods we will see more in details. Like one is DCAO, of course, because we will have the notebook in the afternoon, and Alexander also posted on the WhatsApp already, like about the competition and so on. So have a look, because maybe you need to sign up to weight and biases, and so yeah. About backend methods, no? Like I mentioned that, okay, we can have front-end methods where we deal with noise, reverberation, and multiple speakers with another model that is put on the front of the ESR model, and we do separation at the feature level or at the signal level, and so on. We apply beamforming, etc. But backend methods, we actually try to deal with the ESR only, or at least with the integrated system, like with ESR. Like, for example, already Yoshiki mentioned that he had a great discussion with Professor Hermansky about, he was able in one of the works to just make it work with less data, because he used a pre-trained model like WaveLM. So we will see, like, robust features, robust representation is key to have for decent performance, I would say. And there are other methods, like we can basically get away without speech separation. Sorry, Yoshiki. But no, I mean, I worked on speech separation. My PhD was in speech separation, but yes. And basically do everything with the ESR model. Like, we don't do it explicitly. We just don't care. Just make the ESR model do everything, optimize everything end to end. So because then we can train with in-domain data. We don't have to use synthetic data for training the speech separation model. And of course, there are also more very recently, I would say, other type of backend-based methods that we can use for handling multiple speaker speech, which are LLM-based. So it's the very active area of research. Like, there are some works like diarization LM, or NVIDIA-based one, like, which is very similar. Another seal, which was presented at this ICASP a few months ago. So basically, they rely on this principle that, well, LLMs have been trained on tons and tons of text data. If we have a word salad of mixed up words from multiple speakers, we can probably fine-tune it, or even do in-context learning to just do reassignment and assign those words to speakers. No, we just it's a puzzle. It's a word puzzle, a bit problem, and LLMs can do that to a certain extent, of course. So about robust features and large-scale training, there is no way to get around it. I mean, it's I don't know if you're familiar with the Bitter Lesson blog post from Richard Sutton. He's a reinforcement learning pioneer, no? He basically argues that, okay, it's better to focus on methods that allow to leverage lots of computation and task data. And yeah, we don't have to worry too much about a priori knowledge and so on. I mean, it's both things are true, like, but yes, data matters a lot, and this has been known for decades. Like, the multi-condition ASR training, like you would take before like maybe 10K hours of data 10 years ago, 15 years ago at most. Now it's like 1 million hours. we are able to scale a lot more now. And it's getting viable also for academia, I would say. Like, I think with new GPUs, some models like Open Whisper style model, for example, we can train in few days with one node. So with new H100 on 100K hours of data. So it's getting more and more viable, I would say, to also train your own foundation model and so on. But there are two main approaches. One, of course, is the lazy mode. You don't need tables, no? You just do SSL representation learning. I mean, it's not lazy. Those methods are really smart, but it's easier to do. It's easier to scale, right? You don't have to do filtering and polish the labels and so on. So, and these models, I will give a brief overview about best RQ. It's RQ stands for a random quantizer, and best stands for BERT-like speech pre-training, and so on. And it's very simple ideas. Those models are actually, the core idea is very simple. It's, okay, let's take a speech problem and translate it into an NLP problem in some way. And the best RQ does it in the most basic way. They take speech features, like filter banks in this case, and they apply a random projection. They have Gloro initialization and so on. So it's very simple. Random. They take a PyTorch dot and n dot linear. That's it. And then they quantize the output of this random projection. And there is some way to do that quantization and so on. And then they get for each frame basically a code word, a cluster centroid. And then just mask the spectrum and try to predict the missing frames, the labels of the missing frames, and so on. And this works pretty well. So it scales beautifully. Like in our group, we were able to scale like the Xius model to 1 million hours data with multiple languages, and it works pretty well. And it's very simple. Just collect data, and then it's a matter of compute, no? And other approaches are more difficult, like Whisper or Awesome V4 or the new NVIDIA Nemo Parakit. Is you have to have some weekly labeled data, or it's actually supervised training. And to give you an idea, like I will not torture another time your ears with these challenging data sets and so on, like Mr. Six and DeepCo and Chime6. But the gain you get from using these pre-trained models is significant. I mean, if you train with filter banks features, so without the WaveLM front-end, you have 54%. You train on in-domain data, like on I think on Chime6, you can train. The training set is very small. You do some data augmentation and so on, and you get maybe half a thousand hours total. So it's not very large data, and of course, like if you don't use pre-trained models, you're doomed. And yeah, like you scale the data implicitly by leveraging a pre-trained model. And you scale the pre-trained model size, you get more robust performance. This is with Oracle diarization, with GSS, the method that Yoshiki explained. Yep.
I have a similar question which I had before. We have 4 different scenario databases.
Yes.
Is WaveLM was trained on each of them, or how?
It's the WaveLM basically it's frozen here. Like you can fine tune it a bit. It will improve performance, but you have to tune a lot.
It's always tuned on a particular scenario.
Yeah, this is tuned. Yeah.
How does it work if it is not? If it's trained on Chime and use it on Mixer?
I think I don't have the results for that. I know that, for example, Actually, okay, I think I have, because Mixer 6, we don't have. So in the case of DeepCo, we have. DeepCo doesn't have a training set in this case. So it's just 0 shot from Chime 6 and Mixer 6. But Mixer 6 is included in the training set, and Chime 6 is included. But DeepCo, it's not. And of course, like it's still worse than Chime 6, and acoustically it should be easier. But still okay-ish, I would say. So, yeah. And as I was explaining before, okay, like we have a robust feature representation, but alone it will not solve the overlapped speech problem, for example, because your ASR will be more robust to noise and reverberation, and maybe better at dealing with conversational speech and changing acoustical environment and so on. But we need a way to deal with overlapped speech specifically. And yeah, one is, of course, like speech separation. And I will briefly now talk about, okay, Yoshiki explained a bit like how these speech separation models, how they work. Like he explained very in detail, like multi-channel, single channel, and so on. But I would want to talk about more onto the high level, how can we apply it to long-form data? Because I'm obsessed with long-form data, no? Like we don't have segmented data, so how we can apply those speech separation models on long-form data? We cannot just, you take your DNN and you just run it on 1 hour meeting data. No, it will not work. It will go out of memory. So one solution is a continuous speech separation. So basically, we take the input and we chunk it, like 3 seconds chunks or 5 second chunks and so on. And we feed it to the speech separation model. And we get, for each chunk, the separated outputs. But there is a problem. It's like it's the fact that these models are trained with permutation invariant training. So each chunk, for example, it's not guaranteed that the speakers are not swapped into the output channels. So one chunk, there could be, I don't know, like me and Yoshiki speaking. I am the red one, I am the blue one. The next chunk is inverted. So Yoshiki is the red one, and I am the blue one, and so on. So we need a way to resolve this permutation across the chunks. And in continuous speech separation, what they do is, okay, we take overlapped chunks, like overlap of, I don't know, like, yeah, you just advance maybe with 20%, for example, or 80% overlap, and so on. And then on the overlapped part, you just compute some similarity score. So you compute the similarity score with the previous overlap, and you reorder based on this similarity score. The similarity score it could be SNR, for example, or it could be, I don't know, MSC, or and so on. It's actually a little bit more complicated to do some scale invariant matching and so on, but it's pretty much it. And this way, you can just stream your speech separation through a whole meeting continuously, pretty much. The thing is that this works to some extent because this is actually, sometimes it's not mentioned in the papers, but if you have silence, you have a long silence, then this reordering mechanism where I compute the pairwise similarity for the output channels and then I reorder based on the similarity, it will not work anymore because if I don't see a speaker within a window, this mechanism cannot reorder it. So you will lose tracking of the speaker. And so we still need to do diarization at the end. So there is so for example, in this paper, they show how to integrate probably speech separation, diarization, and recognition for multi-speaker meetings. And basically, the pipeline is like this. You do continuous speech separation. You maybe have 2 output streams. And then you still need to do some diarization afterwards. Like maybe you extract the speaker ID embeddings for each utterance in the separated streams. But the thing is that since you have a separated speech, then it's much easier. You just, okay, diarization basically it's a VAD plus a speaker ID embedding is the best or the case scenario, no? But yeah, it's, or for example, you can also do before, like since you have separated streams, you can do ASR on each separated stream, and then you do diarization because also you have the text. And this is also, I think, it's very underexplored area. I'm not aware of any work that tried to do that. So the Chime8, not so far baseline, that's the link, for example, of the baseline. They do this. They have the CSS, they have 2 streams, and then they feed it to the ESR system. They get the words, and then the ESR system is whispered. They have also the timestamp for each word. And then from the timestamps, they have a segmentation, and they can extract the speaker ID embeddings and then do clustering and reassign the speakers. But nobody used the LLM, for example, for it. So I think it's very interesting if somebody wants to try, to use LLM to just, yeah, you have separated streams at that point, and then maybe you can do something clever. And yeah, regarding what also Yoshiki said, and he had the awesome demo at the end, the target speaker extraction, no? You condition your separation system with some additional information, like the speaker ID embeddings and so on. It's more advantageous in this case. You do diarization first, and then you just use the diarization information to condition and separation. You don't have to do CSS anymore, right? You have diarization. You have some speaker queue. It can be, there are multiple speaker queues you can use. And then you can use that queue to disambiguate which speaker you want. Oh, I want speaker B. And so the model is informed with speaker B information. And then you get the signal for that, and then you can feed to the SR model. And there are, and you say do the same for speaker A and so on. There are multiple works on this direction. One is guided source separation, for example. Yoshiki explained about the complex angular GMM, no? It works beautifully. It's a GMM method, unsupervised. It works better than any DNN-based method or on par of any DNN method we have right now. And it's from 2018, and no progress has been made. I mean, very little progress. Competitive results with supervised approach, I would say, but nobody really consistently are able to beat guided source separation. And guided source separation, you condition with the speaker activities. For each speaker, you have a speaker activity. Other works which are supervised, they use the speaker ID embeddings from the diarization output. And it's also possible to use enrollment utterance, but enrollment utterance, maybe it's good for personalized speech enhancement, like, I don't know, like a Zoom application or a conference call. But for meeting, you usually don't have enrollment. So this is one example of meeting transcription pipeline. It's the baseline system for the CHEM 7-8. These are challenges. As I said, it uses a guided source separation. And the guided source separation is piloted by a diarization system. There is also channel selection to select the best channel in case you have multiple devices and so on. And the ESR system is based on the results you saw previously, like the WaveLM-based. It's a transformer encoder decoder, nothing really fancy. So yeah, it's a very complex system. The code is open source. It's well documented. It should be reasonably easy to at least to run inference with the pre-trained models. So maybe you can try. And what about I made a short digression on still on front-end methods, by the way, because I wanted to show, okay, there are problems actually when we want to apply too long form data, but I was supposed to talk of backend methods, no? And yeah, what about target speaker ASR? So can we just, we don't do target speaker extraction at all. We can feed the target speaker cues to the ASR model, right? And at that point, the ASR model can do it implicitly. the separation and extract the speech from to recognize the speech from the target speaker. And so there are two approaches for backend methods, right? One is target speaker methods. As I said, you have a queue and you condition the ESR system. Others are end-to-end methods. And one popular end-to-end method that we'll cover briefly is serialized output training. So, and compared to front-end methods, the advantage is that we can train within domain data. We don't have a domain mismatch problem. And this is a huge advantage. This is a huge advantage because synthetic data can have some problems. Like we can use for pre-training and stuff, but front-end methods, we have to do end-to-end ESR adaptation. There is no way to escape it. Like if you want it to work on a real-world data, and if your method doesn't employ MVDR at least, you have to do end-to-end adaptation. And these are end-to-end methods by themselves. They don't need. So you can just train it with your in-domain data. So yeah, I will cover briefly like what's serialized output training, and it's basically this. So you just do implicit speech separation, and what you do is you have a sequence-to-sequence model. You can predict speech from multiple speakers, right? You have multiple utterances from 3 speakers. And then you can just, okay, let's find a way to encode the multiple speaker speech, and then train the ESR system to predict it, no? And one way to encode it is, I can enforce some rules. Like, okay, the first speaker, that's speech first, it's first in, first out, right? I order the text like this. Speaker 1, because it speaks first. Speaker 2 speaks second. The utterance comes second. Speaker 3 is the third one. And I put the utterance in this way, and so on. And the model can learn that. These models, deep learning is very powerful with enough data. So and what they do in the original work, which is serialized output training for end-to-end overlap speech recognition, is instead of having explicit speaker tokens, they have a speaker change symbol. So they don't care. They don't give absolute speaker IDs. They just have the model should predict this symbol every time that the speaker changes. So it cannot do speaker attribution in this way. It needs some post-processing at least. And yeah, you basically the original work also they put all the speaker all the speaker that speaks first, all the speech that it's in the input signal, it's put in at the beginning. So I don't know, this speaks here, this speech is good, sure, it goes first. So it was made in this way, I think, because they didn't want to, they still want the model to have it's advantageous from the language modeling point of view, I would say, than splitting in multiple scattered elements, I would say. Because one of the problems with this method is like data. We don't have lots of data to train them on. And they need lots of data because they are trained on multiple speaker. They are trained to predict a very long output, right? It's like almost like a LLM and so on. But we don't have enough data like LLMs. So it's a problem of these methods. But still, they can work also really good with enough data and synthetic data and tricks. And another possibility is to have a speaker tokens. So you just have an explicit speaker token instead of a speaker change. And it was done in this work, but there are other works that try this approach. And in this way, you can do speaker attribution. So it's more end-to-end method than having speaker changes. But there is a problem still. We have the same problem as permutation invariant training, because unless we can apply this model to the whole 1 hour recording, suppose we apply it to, I don't know, different windows, because we don't have infinite memory. And so we need to apply, I don't know, we apply it to the first 30 seconds, and then I don't know, we have another utterance at the end of the meeting, another 30 seconds, and so on. The models are trained to predict the speaker 1 is the first speaker on each segment. So here speaker 1, is the green speaker, and speaker 1 there is the blue speaker. There is an error in my slides, I think. But yeah, this should be the speaker 3. But anyway, it will be flipped, the color. And so we need a mechanism to resolve this ambiguity. We need a method to, in some way, do speaker attribution at the meeting level. We can do speaker attribution at the local level, because I know that speaker 1 is different from speaker 2 in both, but we cannot assign absolute speaker IDs that are consistent in the whole meeting. And so what we can do is just, okay, let's use clustering. So this is from slider work. It's one of my works, and basically what we did is just, okay, we have a model that is like trained with the serialized output training objective to predict the relative speaker ID tokens. So speaker 0 is the first speaker that speaks first in the first window. Speaker 1 is the second speaker that speaks in the first window, and so on. And in each window, this ordering is consistent. And then you predict also timestamp tokens, like Whisper. This is nothing new. But on top of that, the model also is trained to predict speaker ID vectors. And so you basically can use the speaker ID vectors, which basically are related to the speaker ID, the local speaker ID tokens, to reassign globally the identity of the speakers. Because you can run clustering. Like speaker 0 corresponds here to the blue one. And speaker 0 there correspond to the red one. And so you can just run clustering, and you will figure out the assignment, the correct assignment over the whole duration of the meeting. And I call this a quasi end-to-end meeting transcription, because it's not really end-to-end meeting transcription. It's quasi end-to-end because you still need clustering. And the model basically learns, it's nothing more fancy. You have an autoregressive decoder. It's a transformer encoder-decoder model on top of WaveLM features, because these days you have to start with pre-trained models. And the ER decoder is a serialized output training output. It just predict the relative speaker ID tokens and the timestamps and the words for each speaker. But then it has another output head, which predicts speaker embeddings features. So, and this output head is used at inference time to do the clustering and reassign global speaker IDs. So if we don't want to use clustering or deal with this weird permutation problem, we basically need to do a target speaker ASR. And the advantage is like target speaker extraction. We just do diarization first, so we don't have to deal with it later. Because clustering is in some way as okay, we do recognition and local diarization first, and then we need some global diarization and so we do clustering to reassign the speaker IDs. But here it's fine. Here we do diarization first, and like Federico Landini explained how to deal with the diarization last week first, and then we can apply target speaker extraction and do ASR. Or we don't do target speaker extraction, and we just feed the diarization result to ASR system, and we get target speaker ASR, which again we can optimize within domain data, and it's more simple because we have one less component at least. And it totally works the same as the target speaker extraction. We get cues from each speaker from the diarization output, and then for each segment, we just feed the cue to the ASR system, and the ASR system will recognize the target speaker, hopefully. So this is how, for example, very brief sneak peek on how one of these powerful model works. This is the DCAO model. It looks very complicated, but actually it's very simple. Like you do diarization, and this is not shown, diarization, and then you get speaker activities. So these are the speaker activities. For each speaker, you have a mask, and when there is 1 here, it means that that speaker is active, and so on. And when there is 0, that speaker is not active. It's basically like this. And then you feed that mask to the ASR system, and you have some transformation layers, and you condition the transformer blocks with to basically hack whisper to recognize only the target speaker. And this is pretty powerful. Like it works very well. Like why it works very well? Because it's data efficient. No, we don't have much in domain data for meeting transcription. No, it's maybe some 1,000 hours. And then maybe we can simulate data. And then maybe we can add the telephone speech, which is still 2 speakers if we mix them together and so on. We can scale a bit the data. But 1 million hour data like Whisper, it's difficult. So you take a pre-trained model and then hack it to do target speaker extraction. It's pretty smart. And yeah, serialized output training models, fully end-to-end models. Yeah, you can hack a bit Whisper to do that, but it's much more difficult. You need more data because you are modeling jointly all the speakers. In this case, you're just masking the activation a little bit, you know? So it's easier. And one of the reasons it also works very good is that some works try to use speaker ID embeddings to do the conditioning. And the problem with that approach is that you can overfit the speaker ID embeddings, because speaker ID embeddings are discriminative of the speaker identity. So if your model doesn't see as many speaker diverse during training, it will overfit those speaker IDs. It will remember that and will not generalize to new speakers. So
probably everybody knows but me. How do you hack Whisper to focus on a single target speaker?
Yeah, I think Alexander will explain better. But basically, I think they tried different approaches. So they even tried a very vanilla approach. They tried to basically, I think, feed this mask directly and just mask the activation. It still works to some extent. And now what they do is they have a more refined mask where you have a silence, target, and non-target, and overlap. It's a mask which is it's combining all this information, and then they feed this mask to a linear transformation. Then they use this linear transformation to bias the activation, and it works very good. Like
is the speaker ID part of the Whisper?
No. So this is interesting stuff. Like I think there is a paper. This paper basically I don't remember exactly the name, but this paper they explored Whisper for sound event detection, which is crazy because it's a ASR system. And in this paper for sound event detection, Whisper works surprisingly good for sound event detection, but they tried a bunch of downstream tasks, and one task where it doesn't work really well is speaker ID. So it's the only task that it doesn't really work really well. Sound event detection is a bit surprising, but maybe not, because I think maybe Whisper is biasing some some ASR like predictions on the sound acoustic environment. I don't know, like it can, maybe it learns that it's in a kitchen and then somebody will say knife. I think so, but speaker ID, no.
I was going to say, Inek probably is looking for a much simpler intuition. So imagine if I gave it a little audio cut in which you speak for 5 seconds and I speak for 3 seconds. What Whisper would normally do is it would transcribe what you said, followed by what I said, and they're not overlapping. So you give it the same signal, but you only give it your transcript as the target, and you give it a bitmap that says when you're speaking. So that when it hears my speech, it hears the words, but there is no output to produce because there are no transcripts for what I said, and the bit mask is zero.
Yeah.
So between the two, it figures out that it should look at the mask. And of course, the mask may not be perfect. It might clip a little bit of your sound or have some extra bits from me. And it learns the noisiness of the mask. So it's a very simple idea. It simply says, give it the transcript of one speaker at a time, even though the input has multiple people talking, and then give it a bit mask to help it focus on where that's.
Yeah. Yeah, it's all you need is a queue and then some fine-tuning data, and then it can.
Require that adjustment.
Yeah, basically, yeah. But the advantage is that you need very little fine-tuned data, like compared to serialized output training where you need several tens of thousands of data because you're jointly modeling all the speakers, and otherwise you're doomed. But yeah, the disadvantage is, of course, like you have error propagation from diarization. Like if you screw up your diarization output, you screw up the recognition. But I know that we are working on that direction. There are some works, like for example, you can do augmentation on the mask a bit to make it more flexible and so on. Or we are working towards doing end-to-end back propagation through the diarization system. And another disadvantage, maybe it's not really a disadvantage, but you need to perform one inference pass for each speaker. While the SOT system, you get all the speakers in one pass. Here we will have to apply multiple times Whisper. So yeah, to summarize, I think it's, I was very polemic at the beginning, because there are some claims, ESR is solved, it's not solved, and I think now it's a crazy time to work on it, more than ever, because LLMs enable new speech applications, and every day you have a new idea and so on. It's quite going very forward, the field. Integration with summarization, I think it's very interesting. End-to-end speech summarization could be very interesting. But yeah, maybe Ramani or Santosh will on Friday will explain. Maybe it's one task they want to focus on. So I don't know. And yeah, it's robust automatic speech recognition is, as I explained, it's a complex problem, and you need to tackle the problem.
I thought the last speaker, so the speaker before that, said that ASL was sold 9 years ago.
Yeah, it was me.
But you said in the last lecture.
I'm joking. I was joking because it's every time like this. They have these sensationalistic headlines and so on, but the reality is much more complex, and it's we are quite far. No, we will be solved at the end of this workshop. I think so. No, I'm joking.
So I understand that in situations with lots of noise and difficult speakers, it still isn't solved, right?
Yeah, it's very difficult. I think maybe close talk with the phone and speak with the phone. We are quite close. Maybe that is very reliable, I would say. And on those applications, it's more. I think the error is often the transcription is very good, but the assistant or the LLM screws up the action and so on. That is more difficult, I think. But the very close talk, pre-segmented ASR with keyword spotting, there is also tons of data to solve that problem, because companies have been scraping data for decades now for that particular problem. But meeting, no. So it's also a data problem, I would say. So yes. But yeah, so when there is not enough data, you need a priori knowledge. So yeah, like front-end processing, like beamforming and so on. And Yoshiki explained it a little bit. And particular techniques at the back end, and also, yeah, there are interesting works with LLMs that can be done, like especially in the post-processing. And yeah, regarding front-end techniques, like I think Yoshiki explained a bit, like permutation invariant training objective, like MIMO iris, no? The MIMO iris approach, where you have this permutation problem because you're trying to predict the two outputs and so on, and then you need to continuous source separation. And the target speaker extraction, like GSS or target speaker separation, and non-neural and neural model. And you don't have permutation invariant training problem. You just, you're back to the pre-segment, because you do the diarization first, so you're back to the short form recognition in some way. And he also explained a bit about multiple channels, and fine-tuning is crucial for front-end techniques. Everybody does it. Like from result of the CHIME 7-8 challenges, everybody that tries to use DNN-based techniques, they have to fine-tune with their SAR system. And that is very complex to do, usually. It's a huge system, a huge pipeline, and it can be done, but it's difficult. And regarding backend techniques, I explained a bit about serialized output training and the fact that you have this permutation ambiguity also in this case. It's basically the same stuff. And you have to resolve this permutation ambiguity with clustering, with some post-processing, like it's a post-processing diarization. And they are data hungry. And so target speaker ASR right now, it's more promising, I would say. And maybe I am biased, but it's more promising. It's working really well right now because it's straightforward for long form, like target speaker extraction. And it requires accurate diarization, but it's still pretty robust. With if you fine-tune the system with the diarization outputs, it's still pretty robust. So I think Alexander has some. You guys have results on the latest challenge, and you fine-tuned on a real-world diarization, and it's very robust at that point. So maybe 2 words about some maybe trends in the field. It's like one, it's integration, of course. Like we are working towards it in this workshop. Like end-to-end meeting transcription. At most, I can do quasi end-to-end with clustering and so on. This remains how you can do like really end-to-end meeting transcription. How you can jointly optimize, for example, the transcription. The output of the transcription, for example, for long-form data. Like, this is interesting question, I would say. Like, how you can, because, for example, this model I used 2 disjunct losses for the speaker ID and for, of course, like for the decoder model. But how you can maybe, I don't know, like make the speaker ID discrete, and then you can jointly optimize everything. I know that like Gemini can do it, for example, to a certain extent, like because it can ingest very long audio. But then I looked at the outputs; it's very bad. It's thrown to hallucination or very long form data. But I think it's an interesting direction, and we want to explore that. We want to explore like how to try to be more end-to-end. Like maybe fully end-to-end is too much. Maybe we want to just, what we will try at first, we have some models already, like just fine-tune the diarization system with DCOW, for example, and then do back propagation through it. Maybe we improve results. Maybe we'll overfit the training set, I don't know. And another exciting direction, I think it's everything is getting more integrated, even with the speech LM, audio language model. So I think on Friday, like Ramani or Santosh will give a lecture about that. But here the key ingredient is, of course, like the speech encoder. how to deal with very complex audio environments, because then we tokenize. It's a chicken and egg problem. You can compress when you know what's the target speaker, or what is the information, no? And what is noise. But if you want to retain all this possible information in the speech signal, then you cannot really compress. And to understand like general audio, it's maybe you need before to know which could be interesting into the speech signal or the sound scene in order to be able to tokenize it. I don't know, like the speech encoding, it's very difficult problem, I would say. And then, of course, like another trend, I think it's getting more data. And yeah, these are a bit biased because I did some work in the past. Like I think with the new generative methods and the play your part team is going to work on it, they're getting very, very good. And the generated data, it sounds incredibly realistic. Like this is an example from a previous work I did. And we trained a conversational TTS system on 100,000 hours Spotify podcast dataset, and it sounds.
I'm like what's going on?
Yeah, like we're sitting there, and you're like, "What's going on?" And I'm like, "I don't know, man. I think we're just, I don't know. Like, what are we doing, man?"
Yeah, like we're just sitting there, man.
So it's pretty realistic, and the transcription is fake, of course. It's generated with LLM. So, and we showed that you can improve multi-speaker ASR with this data. So you can just generate the data and improve ASR, use LLM, generate the data, improve the ASR system. Then you do inference with the ASR system, you do filtering, you get more transcription and pair the audio data, and then you train your TTS system, and then hopefully you can continue, no? And in some way, it's what we did, because we took the transcription from the Spotify podcast data with a fine-tuned whisper model for 2 speakers ASR. It's a serialized output training model. And then we just used the transcription to train the TTS system, and then we retrain it on other data. But yeah, I will not explain it in detail, this work. So it's a bit out of scope, but yeah. These are some references, like there are links through the paper. There is some review work. This is a recent review work I did. It's on Google Drive now. I have to put it on archive. It's 70 pages. It's a bit too much, maybe. But yeah, yeah, some contact info, and yeah, I don't know. Let's say if you're too hungry or. Do you have any questions? Like, or yeah. No, it's a meme. No, perché? Yeah, my girlfriend cat is similar, though. I always complain. She feeds her too much. But yeah. Yes, maybe I stop the cat. Yeah.
But do you know any approach? Because one of the applications that you mentioned is meetings, for instance.
Yeah.
And you need, like, maybe, I don't know, maybe you need some real-time performing system. Do you know any work on that direction, like streaming?
Streamable? Yeah, there are. Yeah, one is like a CERT, for example, or CERT 2.0. They basically train a transducer to do multi-speaker ASR. I think, the challenge with that is mostly like speaker tracking, I would say, because you need to do the clustering online at that point. And the performance, I think CERT could be scaled. They didn't explore in the paper like CERT 2.0. It could be scaled theoretically, but yeah, I think it was never done, only because I think the offline models are still quite underperforming. So the TCP, the CPWER error rate for these models are usually like in the 50%, even on not very difficult data. So it's a very challenging problem. But for some application, it would be great, no? Like audio captioning for people with hearing loss. It would be great. You have glasses, you can have subtitles, or even, like machine translation, you can have subtitles. But we are a bit far from it, I would say. But it would be cool, though.
Okay, thank you.
I'm wondering if there are any like models that do more like phonetic transcription that can get, I'm sure like in many of these models it's sort of latent, baked in, and you can't like pull that out, but are there models that can like pull out more phonetically transcribed that can capture like individuals, like everybody pronounces things differently in their like individual pronunciation.
Oh, yeah.
So like whether accent or idiolect or however you call it, like.
So I know that my advisor basically is working on that with another colleague from CMU. It's called the POSSUM. Like it's a phonetic open whisper style model. I don't know if, but they are working on it. Like it's a current work in progress. Actually, like they try to come here like in the workshop for that. And they are trying to, like there is Whisper. They are trying to create a large-scale model for phonetic-aware transcription, like at different levels, IPA or and words and so on. They try to have hierarchical CTC to predict different granularity of text information. The problem is data. I think they may have now 10K hours. So the problem with that is data. That's unfortunate a bit. But I don't know, I think you can do some weakly supervised approach where you just extract the phonetic information with some handcrafted method from existing corpora and so on. But yeah, but it would be interesting. I would like to see that. Some applications are like these arthritic. You can have zero-shot applications for that, like these arthritic speech and so on, like assessment and so on. So their goal is mostly for that.